Hello, and thank you for joining us. We will be starting right at the top of the hour. So we got about 3 minutes of 3. Hello, and welcome to Renewable Technologies on the Horizon. This is Dominic Libertor with CPI. I am Logistics Finance Officer for them. I will be going through a few housekeeping items before I hand it over to our moderator. First off, for those of you who are just joining us for the first time, what is NARUC? This is a nonprofit organization founded in 1889. Our members are the state regulatory commissioners in all 50 states and territories. FERC and FCC commissioners are also members, and NARUC has associate members in over 20 countries. NARUC members regulate electricity, natural gas, telecommunication, and water utilities. And then, what is the department we work for? NARUC Center for Partnerships and Innovation. Essentially, we're a grant-funded team dedicated to providing technical assistance to our members. CPI identifies emerging challenges and connects state commissions with expertise and strategies. CPI builds relationships, develops resources, and delivers trainings. And you can check out our website seen here as well. For our webinar logistics, just to let you know, we are recording the webinar and it will be posted to our webpage. And because of the large amount of people on our webinar, we have everyone in listen-only mode. So if you have a question, please put it in the questions box. Our moderator there will be some time in between each presentation, but the majority of the questions will be answered at the end of the presentations. So we will have around 5 to 10 minutes for that at the end. Now I will hand it over to our Commissioner Maria Bocanegra from Illinois. Commissioner, please take over. Thank you.
Thank you so much, Dominic. Please let me know if anybody has trouble hearing me. Before we start, I'll keep this quick. I just want to thank, obviously, NARUC'S CPI for once again inviting us to co-host this. Special thank you to Dominic, Danielle, and Carrie, and everybody who's helped us put this together. Special thank you to our speakers. We think we have a great lineup for you this afternoon. And as always, thank you to my advisors, Jenna and Alejandro, for always doing such a great job helping putting this together. So I'm not going to go through the bios for each of our amazing speakers. You can find that in some of the documents we've uploaded for all of you to view. We'll just jump right into it. So our first speaker today is Jason Feldman. He is co-founder with Green Era Sustainability. He will be talking to all of us about renewable natural gas. Jason, whenever you're ready.
Yes, thank you, Commissioner. Good afternoon, everyone. Thank you for having me here today. I'll be talking about Green Era and how we will transform waste into energy, food, jobs, and healthy neighborhoods. Next slide, please. We created Green Era to change how we think of waste, how we grow food, and also how we create energy. Green Era was originally created to address the lack of availability of nutrient-rich soil in urban areas needed to support local food production and urban farms. We have a huge food waste problem in the US. It's one of the most under-recycled components of the waste stream. It's the #1 item sent to most landfills, and almost 100% of food waste is landfilled. Next slide, please. Our solution is anaerobic digestion. Essentially, anaerobic digestion is just really a fancy composter. It's a very safe and proven technology. There are over 10,000 facilities, anaerobic digesters in Europe, and hundreds more here in the US. And essentially, ADs allows us to safely and efficiently recycle food waste to create really two things. One, to create nutrient-rich soil to support local food production in our project, and also to capture the energy produced from the natural breakdown of food waste. Next slide, please. This is an example of a community digester in Europe. As you can see, it sits in a very urban, dense area as well. Next slide, please. Closest to Chicago where we sit, the closest digester is actually in downtown Milwaukee behind the Potawatomi Casino, right next to Marquette University. This particular digester takes a lot of organic waste from the casino and the many restaurants, as well as Marquette University and other food and beverage manufacturers. They convert this energy into actually electricity to run the casino. Next slide, please. This is the Green Era Renewable Energy and Urban Farming Campus, the project that we are developing here in Chicago. And essentially this project marries both the digester, urban farming, local food production, and a front community area where we will have many different activities. The actual digester itself, the way the sort of process works, is you see that red line there, there's almost 2 hemispheres to our site here. So the top hemisphere where you see the red is more the industrial side, where the blue line is more of the community activities. And essentially how the process works is that trucks will come in, they will come into the facility. The facility operates at a slight negative pressurization, so no odors from the inside come out, only air from the outside goes in and is processed through a biofilter. In the facility, we will have a depackaging operation, so it allows food waste to come in that doesn't have to be super clean, meaning we can depackage from packaging, whether it's cans and plastic, oranges and netting, which makes it very easy for folks to divert to us. After it's depackaged, it goes into the digester tanks. You can see there in the back there. And essentially the digester tanks are just a big tank that operates in the absence of oxygen. There are microorganisms in that tank that break down the organic waste. It's a natural process. And then it creates those 2 byproducts. One is the renewable natural gas, which will be injected into the local gas grid. And the second is the nutrient-rich material. That nutrient-rich material or compost will be used both on the on-site urban farm and our other farms throughout the area. And that the food grown both on-site here will be sold at the front community area where we will sell not only the fresh healthy food we're growing, but native plants. And there will also be an educational facility there to really connect folks very tangibly to sort of the closed loop cycle of what we're working on. Next slide, please. So this is just another shot of sort of the front community facing area. Another shot there. Currently, we live in a very linear economy, which is truly unsustainable. What I mean by that is this is where we take a resource, we make something, and then we often throw it away. And it truly is critical for long-term sustainability to decouple this economic activity from the consumption of very finite resources. Next slide, please. And this is what we plan to do with the Green Era model, to demonstrate how we can create an urban circular economy, to divert organic waste, which is truly a resource, from landfills, to create clean, renewable energy, rich compost to expand our local food system, which in turn creates more local jobs and drives economic development. Next slide, please. Urban Growers Collective, our nonprofit partner, has demonstrated for over 20 years the tremendous impact of expanding our local food system. We have over 8 farms on over 11 acres, predominantly in Chicago's South Side. These farms are typically in highly distressed areas where industry is left, leaving a void of jobs, opportunity, and hope. Most of these farms we're setting up with on industrial sites, we have to bring in tremendous volumes of soil, and that's a real bottleneck for our expansion, but also for the many folks that we train at our sites to farm throughout the city in community gardens, different urban farms as well. And the digesters compost provides that catalytic input to expand the local food system and to help drive critically needed neighborhood-based economic growth. This also supports important programming that we operate via the nonprofit. One is Grounds for Peace, which takes city-owned vacant property in high crime areas, working with the Chicago Police Department as part of a solution to reduce violent crime. You take these vacant lots, you begin to beautify them, and violent crime begins to go down. So we're working directly with the mayor's office and the police department on that. The second on the bottom right there is an initiative called Fresh Moves. We're working again with the city. We take decommissioned Chicago city buses and outfit them as mobile farmers markets to distribute the fresh, healthy produce that our nonprofit grows to food desert communities. So it's fantastic for us because it allows us to get our product out to folks who need it most, and allows us to really efficiently get it to food desert areas. It's expensive, it takes a long time to build supermarkets, but having something like this allows us to truly target areas that critically need access to fresh, healthy food. Next slide, please. Now we've talked about the soil and why that's so important. Now, what is RNG? RNG is renewable natural gas. Is natural gas that is produced from the decomposition of organic waste material. After treatment to remove some CO2 and other trace constituents to meet pipeline quality specifications, at the end of the day, RNG is mostly methane. RNG is a low carbon, often carbon negative alternative to fossil-derived conventional natural gas. And this is really different. If you use a waste product like food waste to produce renewable natural gas, it actually has a very low negative carbon value. Next slide, please. Now, sort of natural gas versus RNG. RNG is produced from the inevitable organic waste streams that emit methane during decomposition. Natural gas is collected from limited fossil resources that would otherwise remain sequestered within the earth. And utilizing waste methane as RNG reduces greenhouse gas emissions from both waste generation and the fossil fuel consumption. Next slide, please. So where is it being used? RNG uses existing natural gas infrastructure for transportation, dispensing, and consumption. So you don't need to upgrade often the natural gas system. It can directly tie in. It's most commonly used in heating applications and combined heat and power units to generate electricity, and as a transportation fuel, which we'll be using. It is interchangeable with conventional natural gas, providing a pathway to decarbonization, whatever energy demand exists. So it's very flexible. Next slide, please. The economic impacts are also very powerful. The RNG industry has experienced unprecedented growth in recent years. There are over 129 operational facilities in North America, with many, many more in construction and near completion. And RNG has the potential to create millions in capital investment per project and thousands of jobs as well. Next slide, please. This is just a map from the Renewable Natural Gas Coalition that sort of outlines where many of these projects are. And again, RNG demand is growing in more states, cities, and companies as they seek to decarbonize their energy portfolio. So these are just some slides and different companies that are often transitioning to renewable natural gas. UPS is one of the biggest buyers out there. They have a huge fleet of CNG vehicles, and now are transitioning most of the fuel consumption in these CNG vehicles to renewable natural gas. So it's a very easy switch for folks to make. Next slide, please. We need a, RNG is part of that solution. This isn't a silver bullet, but it is, part of the solution. We need a diverse portfolio of solutions to address environmental challenges like decarbonization. And RNG can play a very important role as part of that solution. It provides a local and renewable supply of gas. It enhances system flexibility. It allows communities, businesses to embrace environmental sustainability, and it truly allows customers to make an impact. They can choose in many states to buy renewable natural gas. And this is all without new pipelines. We have the infrastructure that we can directly tie into. Next slide, please. And now more than ever, projects like this, solutions like this are important. The pandemic is impacting our global food system, spotlighting the need to expand local food systems and also upgrade our infrastructure. And this project will directly help that. It'll help expand our local food production, improve food security and nutrition. Also has the benefit of reducing climate change impacts and creating jobs in underserved communities. We have an incredible, efficient system in a lot of ways, but it is also very fragile. We also have some exciting news. Earlier this month, we had 3 exciting announcements. 1, we broke ground on the project. 2, we are the recipient of we are honored that our team is the recipient of the Chicago Prize, which is a $10 million award by the Pritzker-Traubert Foundation to a community-led initiative on Chicago's south and west sides. Next slide, please. We were also awarded a $2 million investment from the state of Illinois and had an amazing, as you can see, socially distant press conference with the governor, the mayor's office, and a host of elected officials and community members. Folks are very excited about this project. We are grateful that we have incredible momentum and support, and I believe this is really truly emblematic at a time of collective distress and how innovation can inspire transition that will drive beneficial change in communities, the environment, and our energy infrastructure. Thank you.
Jason, thank you so much for your presentation. We do have a couple of questions I thought I'd share with you. The first question for you, Jason, is from Donald. Is it digest batch or continuous?
So it will be continuous.
Great. One more question here. Is compost or RNG the most significant product?
It's a great question. I guess it depends, who you're talking to. For our urban farming operations, the compost that is a critical input to expand our operations at the nonprofit, critically needed by the community, and a huge jobs creator. But most projects out there find that the revenue for supporting projects like that, renewable natural gas is a bigger driver. But it's sort of that collective benefit of all those pieces that I think makes these projects so powerful. It has lots of benefits to different stakeholders.
Right, absolutely. And this is somewhat of a question, but they want to have your contact information, Jason. So we will be sure to share that contact information for Green Era with all of you. I'll type it in the question box. You can also find it in some of the documents we've uploaded. But those are all the questions for now. I think we'll go to our next speaker. Our next speaker is Cristina Negri. She is with Argonne National Lab, and she will be discussing agricultural advances in the renewable technology space. So Cristina, whenever you're ready, thank you.
I am very ready, and thank you very much for your introduction. Thank you everybody for listening to my talk today. I am the director of the Environmental Science Division at Argonne National Lab. We are located 26 miles outside of Chicago in Lemont. And I just want to say I'm speaking here for a large team that is really working hard on topics that I'm presenting today. Next slide, please. I thought I'd start giving you an idea of what Argonne is. Argonne is one of the 17 national laboratories that are owned by the Department of Energy. We are sister labs with Berkeley Lab in California, SLAC, Lawrence Livermore, Oak Ridge National Laboratory in Tennessee, and many others, as you see in the map. We are managed by the University of Chicago, so I am not a federal employee. I'm an employee of the University of Chicago. Next slide. And I lead a division in there, which is the Environmental Science Division, which really has to do with major things that have to do with the environment. The first one is Earth systems. We do science and climate in understanding how the Earth works, pretty much. We improve our understanding of climate risk and resiliency, and better understand the effect of climate on our lives. The other parts of our division really has to do with energy and environmental impacts. We look at environmental impacts for a number of energy applications, whether they're renewable or non-renewable, and we provide science-based solutions to mitigate unwanted impacts. The one I wanted to talk to you about more today is this idea of responsible innovation, where we really drive new discoveries in the use of natural resources toward responsible outcomes. What it means that we think before we offer a solution that may be economically valuable, to look at it throughout the environmental lens. And next slide. That actually brings us to ask different kinds of questions. And so in the bioenergy example that we'll give you today, instead of saying, oh, I want to employ crop X because I think it's going to be workable, we really thinking through this lens of responsible innovation, and we say taking care of the future through collective stewardship of science and innovation in the present. We want to be there at the bench of when we all develop new systems, so we preempt some environmental concerns. So we don't ask what the impacts will be generically, but we design from the start for the enhancement of natural capital and human well-being, which really means that we really need to take into account a lot of more factors in designing our innovation. Next slide. Since we are talking about bioenergy and biofuels, obviously, we are dealing with the agricultural landscape and the agricultural realities of the time. We all know how stressed farmers are because corn prices and other commodities prices are fluctuating. They have no control over it. Yet, on corn prices depends rural livelihood. So it's really a difficult equation to balance many of the times. Looming on the horizon, we know that corn, a good half of the corn that the farmers produce, particularly in the Midwest, is really going to ethanol for a gasoline additive. Then what will happen in the future when cars will be all electric? What we will do with all these acreages, and what will we know? How we find new markets for what the farmers can produce? At the same time, growing corn creates trouble, right? We know that there is it's task force looking at hypoxia in the Gulf of Mexico, and we know that a lot of the nutrients that go to the Gulf of Mexico come from Midwestern states and agriculture. Farmers don't really have a lot of latitude to do many things. There's cost associated with them, but our work is really trying to find solutions to those problems. And I hope I can show you in this talk how this dichotomy between economics and environment did not be really. We don't really need to think about that or have those contrasting options if we think of all these issues from the very start. Next slide. So what we think about rethinking the agricultural landscape. To your left in the yellow and green, you see the current land use this is in central Illinois, where we have our field site. You see it's a kind of a binary production. We know that the year one field is growing corn, the next year will be soybeans or something similar. This landscape is focused on, and I'm using the term landscape more broadly, not the landscape in a pretty picture, but really how we use our land and how the land looks like. This landscape is focused on providing one service, which is yield and profits, right? So the farmers need to grow corn, need to sustain their farms. They look at, rightly so they look at profit. Regulating services, which means making sure that the water is clean, that the air is clean, there's biodiversity and all that, are really not factored in this landscape. They're called externalities. The conceptual focus is how to mitigate the impacts retroactively, meaning I grow corn because I need the yield, I need the profit. I'll think about the environmental impacts later. It's a non-diversified business model. It concentrates risk on a couple of crops, and even though farmers have crop insurance, generally speaking, it's obviously very vulnerable to environmental impairments, whether there's a drought, whether there's distributed flooding, whether there's a pest coming through. It's all our resources are thrown into a very non-diversified portfolio, and that creates vulnerability and less resiliency. On the other side, if we think of a mixed landscape, we think of really producing not only the crop we want to produce, but we also think about how to positively impact the environment, optimizing water quality, optimizing habitat, for example, for hunting and recreation, or biodiversity, optimizing carbon sequestration, which is something that we have to think about now if we want to avert a true climate crisis. We think about flood control, reduction of greenhouse gases, etc., and we can think of those in the design phase. The economic models accounts for both. So we account for the corn, we account for another crop, and we account also for the value of the positive environmental impacts that we call ecosystem services, and the value that they may have. The conceptual model here again focuses beyond just mitigating impacts, is really focused on how to design, right, so that we avoid these impacts altogether. And again, it's a diversified business model. Next slide. So you see that we are going from evaluating the damage to actually improving the capital, natural capital, and the human well-being down the stream. Next slide. So how does it work? And you've seen this, the photo on the right is something that USDA has been promoting for a long time, having a lot of wetland restoration, repairing forests, windbreaks, filter strips, all the good tools of conservation. The addition to this is that if we, in these particular features of the landscape, put bioenergy crops, we actually get a marketable crop. And so the economics look a lot better. There's a lot of things to do with that, including policy and how the conservation programs really reward farmers for this, but conceptually, we have seen that there could be a lot of benefits. You see on the left, the idea is, for example, for nitrate, which is really what runs off the fields from fertilizers, that what gets lost by the corn can be picked up by another crop, like switchgrass, for example, or willows in the other picture. That's our field site. What does that do? It basically provides free fertilizer for these other crops. So you don't have to spend additional fertilizer, plants grow better, and at the same time you avoid a problem in water quality. Our approach is really targeting marginal lands, meaning marginal, what we mean is really that's underproductive or has some very strong vulnerability to environmental damage, and so we are thinking that this would be the first land that we want to consider for this alternative system. Perennial bioenergy crops have a lot of benefits, and I'll talk more about that. And the idea is to place these bioenergy crops strategically to increase the benefits that they can provide. Next slide. So when we talk about perennial bioenergy crops, we talk about willows, which is what we have been studied mostly, miscanthus, Indian grass, poplar trees, switchgrass, and big bluestem, which are native to the area. They have a greater tolerance to environmental stressors than annual row crops. They can tolerate better wet and dry conditions, higher salinity, low fertility, etc. So they are much more robust. They need less fertilizer to begin with, and they can actually rely a lot more on recycling, internally recycling these nutrients. They can provide ecosystem services. They've been shown to provide a different path for absorbing nutrients, but also to provide carbon sequestration and providing a different habitat for different other critters in the field. So the benefits they provide are disproportionately greater than the land that they occupy, and so they can reduce the impact on commodity crop production. And you see some pictures in there. A lot of these crops actually have been developed at the University of Illinois, particularly switchgrass and miscanthus. This is where most of them have been developed commercially as cultivars for broader application. Next slide. So, and I can tell you a little bit about what we're looking at, targeting marginal lands. You can see this is our small sample and test watershed in smack in the middle of Illinois, more or less. We looked at different properties and we came up with a map that really identifies the areas that, and you see them in kind of red and different colors in the central map, to identify which land would be the most suitable for this. And the last picture on the right shows our field site, and it shows the heat map of nitrogen fertilization and how that it is more endangering groundwater when it's really placed on areas of lower productivity, and that's the area exactly we're thinking about. Next slide. We can see that by placing willows in a buffer zone next to that hot spot of yellow and red groundwater pollution, we have in a few years been able to reduce the subsurface water concentration of nitrate. I don't want to go through the details of this. It's obviously a busy technical slide. Suffice it to say that the willows that we've planted in this field in that strategic position really did help with the years as they grew to decrease the concentration of nitrate going off-site and going obviously to surface water bodies as well as groundwater. This is done with field work and collecting a lot of samples, and incidentally we have wonderful students that join us every summer to do this work, and they love it and they really learn a lot. So we're always looking for good students. Next slide. I won't go too much in this. Again, so suffice it to say that willows reduced the emissions of nitrous oxide, which is a potent greenhouse gas. It derives from the decomposition of fertilizers, and so if you make the fertilizer use more efficient, then you have a lower emission of nitrous oxide, and that is a really good thing for the balance of the fluxes in and out, and for the sustainability of these crops. Next slide. Likewise, it's again busy slide, but I wanted to show you that with time, since these willows reach down with their roots deeper than regular corn crops, we are seeing an accumulation of carbon in the subsurface, basically going down 3 to 4 feet. That's good. We are developing carbon quantities and quantitative assessment of how much this carbon accumulation is. But if you are thinking of carbon farming in the future, as is being proposed to mitigate climate change, this is actually a good number to have. Next slide. When I talk about marginal land, what am I talking about? You see Illinois and the classification of land in there. We're looking at crop productivity. Obviously, if in general crops don't produce enough, they are considered economically marginal. But we also look at places where there could be some additional risks. Risk of excessive water ponding, for example. A poor drainage, leaching nitrate is a good one. Leaching pesticides, which could impair our drinking water, and flooding, right? So do these soils drain enough? And that's what we're really looking at, because we know very well that in Illinois there's a lot of use of tile drains. Those are the main exporters of nutrients, and so if we can do something in these soils so that we avoid that total export of nutrients through tile drains, it would be a good thing. Next slide. So what we did is run a model with our field data and other data, and we looked at two scenarios. One is the current land use, which you see on the left, and you see a different land use, which is the one in red that includes switchgrass in this particular case, on these particularly marginal pieces of land and pieces of acreage and so on. And what we did, we used a particular computer model that's called SWOT, which is very common use. And what you see in the slides before is the before and after. Tile nitrate and leachate is decreased over time, as well as sediment yield into receiving waters. And so we think that with a relatively moderate investment in land and land use change within the agricultural system, we can actually impact very positively the quality of the water that's leaving the watershed. We also used another model, it's called INVEST. You see that the fainter image in there. There was a collaboration with the University of Michigan. They looked at what would happen if we had this more diverse landscape, and what would it do to biodiversity, and in particular, pollinator nesting. Right? We all know that pollinators are endangered. We know that they are in trouble, and we wanted to see if just introducing another crop, we could improve their chances of nesting in this particular case. And all you see is that although this landscape is really not optimized for them, just adding an additional crop to the mix and what we have in the landscape, we definitely improve their potential for nesting. Next slide. So what does it mean economically? We did it on a larger scale. You may want to go ahead a little more. Click maybe another time again. Sorry, I didn't realize there was an animation in there. But what we did at this point, using a larger watershed, in which the previous one is nestled, we looked at the revenues from that acreage, that particular set of land. And what we found is we looked at the benefit, not only the value of the crop themselves, but we also looked at the value of that improved water quality in this particular case. And what you see there is that if we changed the landscape to include more switchgrass, depending on the value, the cost of the value of the switchgrass, we would have obviously a decreasing value, but it's more than compensated by the value of the nitrate reduction in there, assuming that there's a trading market to take that. So the actual total value coming out of the watershed is definitely quite increased. Next slide, and I'm almost done. Likewise, for carbon, we have seen that if we looked at different crops, we could increase the amount of carbon. I won't go into detail, but this meant to say that really there is a range of different potential for carbon sequestration, and depending on how one values that, there could be really a significant amount of economic value created in the state, for example. Next slide. What does it mean? It means that our process has on one side a beneficial life cycle analysis. Life cycle is the process by which we analyze the emissions of greenhouse gases from cradle to grave, and that shows that the net emissions from producing willows on this marginal land were much less than those from producing corn on that land, because we minimize the use of fertilizer and farm work, which turn into energy expenditure, which create greenhouse gases. So that's a good thing. And as far as cost per unit of nitrogen removal, it's really comparable with very well established conservation practices: cover crops, crop rotation, wetlands, bioreactors, controlled drainage, and others that the USDA is constantly, letting farmers, suggesting farmers to do. So we're in good shape here. And so we think that because we have this additional benefit of a sellable crop, it could be an easy thing for farmers to do. Any chances this could happen? There have been private-public mechanisms for ecosystem services payment. You see here a few taken from the NRCS Pay for Success program. Basically, it works on the fact that the NRCS is kind of a broker of a system in which there are other organizations like nonprofits or other venture capital organizations that actually subsidize this activity particularly. We have example in Maryland and Delaware and Pennsylvania with the Chesapeake Bay. We have other example in the Ohio River Basin from EPRI and the Fox River Valley Phosphorus Trading Program in Wisconsin. So this is doable. Obviously, it requires some policy and some action in there that goes beyond what we can do in the scientific world, but it could be a good opportunity to turn farmers into producers of food and grain and all that, and also producers of environmental services, which may be helpful in the long term. Next slide. So I will leave you with one slide that really talks about what would be implications for rural economies. We would need to leverage this work to attract biorefineries. It could ease the cost of biomass if we knew that we could sell some of the environmental benefits as well. It could be, as I mentioned, enabling farmers to be energy and environmental entrepreneurs, recognizing a value and a service would bring them back to being players in big problems in the world. We could link to the needs to deliver from the Gulf Hypoxia Task Force. We know that Illinois, for example, has a Illinois nutrient reduction strategy. So does Iowa and other states. So it's a good linkage. And obviously, setting up a trading system will be important. And here is where the utilities come to place. Carbon obviously is of interest to the power utilities. We had many conversations on nutrients and nutrient trading with water reclamation utilities. What if instead of spending money on heavy equipment in the wastewater treatment facilities, we actually thought of letting the farmers do some of this work and removing the overall burden of nutrients that leaves, for example, Illinois. Hunting, recreation, biodiversity, and other ecosystem service could also be in there. So in substance, I think, next slide, that there could be really a lot of benefit if we could explore that from the lens of how practical and how can we make this happen in the field. If you are interested in more information, we have a website where you can actually look at the different aspects of this project more in depth. I just gave you a quick skimming of that, and with that, I will close my presentation. Next slide, it's just acknowledgement. Again, lots of students coming through and a lot of collaboration that makes this work.
Thank you so much, Cristina. I think what we'll do is we will save those questions for the end in the interest of time. So next up, we have Dr. Erdal. He is the Senior Vice President for Water Reuse National Technology Director. So Doctor, I will let you start whenever you're ready.
Thank you, Commissioner. Thanks for having me today. Next slide, please. Before starting my presentation, we know that energy is a very important aspect, important to water generation, but water is also needed for every essential need, energy generation, food crops, everything. So water is very essential and fitting into the today's discussion. Next, please. This is my outline. I'll start with why water reuse, show you water reuse types, some definition and types of potable reuse. We'll make case for direct potable reuse, challenges and implementation consideration, and final remarks. Next, please. Although majority of Earth's surface is covered with water, we have only 2% of that water accessible for human consumption. In urban areas, population are growing really fastly, and current supplies will not meet future demand in most urban areas. Next, please. And prolonged droughts is causing water shortages, and it will be likely more frequent and more severe in future. And discharging treated wastewater containing rich nutrient to receiving bodies are causing red tide and algae blooms. Next. Drought and excessive withdrawal also causing several problems such as depleted groundwater. What happened is if groundwater depleted fresh sources, coastal area, seawater will intrude to fresh supplies. We may see some land subsidence in certain areas and reduction of water in stream and lakes. You can see a picture how much land subsidence occurred in Central Valley of California over the years. Next. Why water reuse? Water reuse is an alternative water supply that is locally controllable, drought-proof, sustainable, and more affordable than many other conventional water sources. It reduces or eliminates discharges to receiving bodies, prevent red tide, algae bloom events, and reduce groundwater extraction, which prevents seawater intrusion in coastal areas and land subsidence in several areas. Water reuse also supports the local economy. Next. So these are the general classification of water reuse, two general categories: non-potable reuse, potable reuse. Non-potable reuse is the use of recycled water for non-potable purposes, such as agricultural irrigation, landscape irrigation, industrial uses. Potable reuse is the use of recycled water for potable purposes. Two major classifications: indirect potable reuse, IPR, and direct potable reuse, DPR. Next. This is the definition. It's a little bit complex, but the difference between indirect potable and direct potable reuse is basically augmenting drinking water source with recycled water, followed by environmental buffer in indirect potable reuse, whereas direct potable reuse, there is no environmental buffer, whether a surface water like lake, river, or groundwater. I will further explain in what exactly it is in upcoming slides. Next, please. This is unplanned IPR, which has been a long practice in United States, especially in Mississippi River area. Unfortunately or fortunately, many people do not recognize their drinking water is supplied through an unplanned indirect potable reuse. How it works? So basically, treated wastewater from a wastewater plant discharged in the upstream of a river, and downstream there is a drinking water treatment facility, take that water and produce drinking water for the community. Many large cities in United States rely on that scheme, such as Atlanta, Philadelphia, Houston, New Orleans. Next. This is planned IPR and DPR. In this case, there is a surface water or groundwater supply source. We can treat that supply source through a drinking water treatment facility. Water is distributed to community. The people use that water, and water becomes wastewater, treated through wastewater treatment facility, and discharges into a receiving body usually. But planned IPR, DPR, we are not discharging that thing to the receiving body. We are treating through an advanced water treatment facility. Next, please. And in IPR case, we are basically putting highly purified recycled water to an environmental buffer, which is surface water or groundwater, before being treated through a drinking water treatment facility. Next. But DPR, again, we don't need environmental buffer. We can put the highly purified water either ahead of drinking water treatment facility or directly put into a distribution system. Next, please. That scheme is called direct potable reuse, or DPR, which is the main focus of my presentation today. Next, please. So why potable reuse makes sense? First of all, non-potable reuse demand is seasonal. So when it is rainy, we don't require any recycled water to irrigate plants, golf course, so on and so forth, which is less sustainable with reduced environmental benefits because we are still discharging treated wastewater to receiving bodies. And non-potable reuse demands are geographically separated by large distances. Golf course may be located in north side of the city, but an industrial facility may be south side of the city. So what it does, it significantly increases pumping and conveyance costs. So potable reuse, that costs significant to reduce, but the biggest dilemma is public acceptance. Public acceptance historically favored non-potable reuse over potable reuse, but it is changing with effective public outreach and education in recent years. Next, please. This is the potable reuse cost versus alternative supply cost and unit cost per dollar per acre foot. 1 acre foot is about 0.32 million gallon. I want you to focus on the blue lines, blue charts. So this is the cost of the main treatment and cost of conveyance, but it's not a significant cost requiring complex conveyance system. Orange line, on the other hand, requiring significant conveyance system, complex conveyance system to distribute or collect the water. So a little bit skew information. So if you focus on blue line, as you can see, IPR, DPR cost, unit cost is about $750 to $800 per acre foot, whereas brackish water is a little bit more than 900. When you go seawater desalination, that costs exceed $1,500. This is California-centric information. Southern California gets water from either Bay Delta area, state project water, or Colorado River water. Blue reflect Colorado River water costs, bringing that cost to LA area, and orange reflect the state project water costs. But again, those are substantially more expensive than indirect and direct potable reuse cost. Next, please. This is the energy requirement for alternative supply sources. The first one is IPR, DPR. As you can see, the energy requirement for IPR, DPR is about 3.3 kilowatt hour per 1,000 gallon water produced. When we go to brackish water desalination, that energy requirement slightly more, about 3.8 kilowatt hour per 1,000 gallon. But when you do seawater desalination, that cost is significantly increased, almost quadruple compared to IPR, DPR cost. The reason is simple, because we are desalinating highly concentrated salty solution passing through a semi-permeable membrane, which require substantial energy. The last two is bringing water to Southern California. State project water require 9.2 kilowatt hour, whereas Colorado water, river water, 6.2, all related to pumping energy costs to bring water from large distance. Next, please. So DPR is not really new concept, but getting traction in several states. Why? Because public acceptance evolving. The location may not allow several IPR projects due to the not suitable location for groundwater recharge, or there is no surface water source available in cross proximity. There is no water quality issues with DPR, and technologies used in the IPR project readily available for DPR. Sorry about, for some reason, the format a little bit screwed. So next, please. These are some project example and benefits. I don't want to show one by one for each. One of the oldest is in the city of Windhoek in Namibia in Africa. So that DPR project was commissioned, the first phase, in 1968, and upgrade was taken in 1997. So that city has no surface water and groundwater to access. It has 600 miles from ocean. So this was the only logical and cost-effective solution for 200,000 people. And the other example is water recycling system at International Space Station. The premature version was basically employed in 2000 and significantly upgraded in 2014. Cost, unfortunately, wasn't disclosed by NASA, But what it does basically, it generates potable water for 7 astronauts. If there is no DPR option at the space station, we can only send 3 astronauts to that station any given time. There are 2 other examples of DPR, both in Texas. Those project was implemented because the drought was very severe in South Texas, southwestern portion of Texas, that provide safe and reliable alternative supply source for each case. Next, please. So you can see the picture on the right-hand side, the space station water generation recycling unit. Next, please. Challenges and implementation consideration in direct potable reuse project, 3 major public, technical, and regulatory challenges. Next, please. Probably the most important challenge is the public perception and acceptance, because perception drives our decision in our daily life and also potable reuse projects. Next, please. But if people understand, public understand that they are already living downstream, and it may be okay with a water solution that includes also planned potable reuse. Next, please. And next. So with good public education, the yuckiness factor of potable reuse will be disappeared. Orange County Water District in Southern California did it, and San Diego also did it with effective public outreach and education. That clearly showed that the produced water is extremely good quality, similar to potable water and bottled water. Next, please. And next. So second biggest challenge is regulatory concern. Yes, the wastewater origin contain pathogenic organism and trace organic compounds. Pathogenic organism is an acute risk concern, whereas trace organic is chronic risk concern. We need to address them. Next, please. How we can address that? Because we are using multiple barriers, multiple processes to purify the recycled water. So for example, ultrafiltration, reverse osmosis, UV advanced oxidations are all very effective barrier for pathogen, and you don't even need tail end chlorination to address pathogenic organism. They are so efficient to do good treatment, pathogen-free, produce pathogen-free recycled water. Next, please. Technical issues, there are many tools, costs, or concentrate disposal in certain areas, source control, but we don't have time to address those challenges. But I'm more than happy to come another time to talk about if there is an interest regarding DPR and technical issues. So final thoughts, recycled water is definitely drought-proof, locally available, sustainable alternative supply source. Potable reuse has several advantages over non-potable reuse because it's non-seasonal, superior environmental benefits. DPR costs are compatible with any other supply sources. Biggest challenge with DPR is to overcome public perception, but with sophisticated public outreach and education, we can overcome this hurdle. Effective source control and enhanced process control and monitoring will improve reliability and public acceptance. And before concluding my presentation, remember, all water used in Earth we use again and again. There is no pristine water. The water we are drinking right now is maybe 1 million years old. With this, I'm concluding my presentation. Thank you for having me today.
Okay, I think that is the conclusion of all of our presentation. Thank you to all the panelists. Very, very interesting discussion. We do have some questions, so I'll go first through the audience questions here. Jason, there's a couple questions here for you. I think I missed them right before I turned it over to our next speaker. The first one is, how much will the facility cost to complete?
Great question. So there's several phases to the facility. The initial phase is $32 million, which we've closed for the facility. There's also some expansion opportunities with the facility, as well as about $5 million additional we are currently working on for some of the community aspects. There's a large educational component to the work that we're going to be doing on the campus in terms of engaging and, as I mentioned, really connecting folks very tangibly, like at a very high level, why should I recycle that banana peel? Why is that important? To really show that full life cycle and how it is recycled, turned into energy, turned into compost, and then you get that fresh, healthy food at the same facility, as well as being able to buy plants and compost for maybe your own home garden. So there's various phases. So we're talking with different stakeholders right now on those sort of secondary phases as we get going.
Thanks, Jason. We have one more for you here from the audience, and the question is, what is an area of opportunity for regulators, utilities, and stakeholders to consider to adapt current regulation for this particular innovation?
Great question, and I think there's a lot of opportunity there. It really starts with education, really showing how this has been successfully deployed both overseas and here in the U.S., and sort of the ancillary benefits that are associated beyond just the energy and being able to tie into the grid to make it more resilient, to allow customers to access renewable natural gas. There's a lot of calls for new buildings, particularly in California, to be not connected to the national gas grid. And I think if we can educate folks to the critical element natural gas still plays in our infrastructure and how renewables can be part of that discussion very seamlessly, is critical. So I think pointing to great successful projects out there, how this has been rolled out, education, and then how it can really drive economic development as well, I think is all part of that. But it's complicated, but I think there's great opportunities in it, and it really starts with education.
Thanks, Jason. Oh, that's a very good point. So I'll turn over to Dr. Erdal. One of the questions we have, in one of your slides, you note that DPR is not a new concept and it's gaining grounds in states like California, Arizona, Florida, and Texas. I think I know why, but for the record, can you tell us why in those states it's important, and how can we make the case in other states that may not experience drought challenges or access challenges?
Absolutely, great question. The reason why Texas, California, Arizona, they are more interested in DPR because they are arid states. The water resources are very scarce in those states. Because of that, the IPR, DPR have been gained so much momentum in that stage. But you are absolutely right. We shouldn't stop there, because that concept is very, very feasible, cost effective, and locally available, much more sustainable. We can easily apply that knowledge to other states. So it's not very difficult to do that, but it's required certain time frame to establish regulatory framework, gaining the public acceptance, so on and so forth. Once you have done that thing, the engineering standpoint, technical standpoint, it's not difficult to implement. It's in fact opposite. It's very easy to implement that thing for other states, especially considering the recent situation in the world, climate variability. We don't predict what will happen to certain specific area. Today, maybe water is plenty, but tomorrow, 10 years from today, may not be the case. So it's important. Very nice question.
Thank you, Doctor. Unfortunately, we are at time. I did not get to nearly all the questions we usually have for our speakers. Thank you, everybody. If you have any follow-up, I think Dominic and the rest of our group here can tell you where to contact our panelists. So I will turn it back over.
Yeah, thank you so much. Thank you for joining us. Just to look at here at our, our upcoming webinar series. We do have one September 17th and another one October 22nd. But please check out our website. You see the site right here. We have a bunch of other ones that we're planning, this upcoming year. So please check that out. And we thank you so much. If you have any questions or if you need to reach out to any of our speakers, I can definitely send you the email. You see my email down here. And then also here's the website again for those of you to check out. So thank you so much, and we hope to see you again.